Hello everybody. I thought maybe it would be a good idea for me to show you one more example of the combined loading type of problems, especially for cross sections that are not symmetric. And you could see by symmetry I mean that they have different, moment of inertia with respect to, like in this case, x-axis and y-axis. So here we have a rectangular cross section which is actually a 4 by 6. So the width is 4 and the depth is 6 inches. Okay, and then as you could see, this rectangular cantilever beam, which is fixed here at the wall, is subjected to three forces here, the axial force, and then these kind of like shear forces at different locations. And our objective is to find sigma and tau at 2 points, point H, which is right here, 1 inch below this top fiber, and point K, which is right here at this location at the center. Okay, so what I did, I just cut this section, right, and showed all the internal forces right in this section of the interest where point H and K are. All right, so what I did, basically what you want to do is just transfer all your forces, the 2400, 1200, and 3600 to this section. So I did that. But remember that once you do that, you have to consider the moment of these forces about different axes. By the way, I call this, as you could see, this is how I labeled it so we can refer to these axes, X, Y, and Z. So the N actually is in the Z axis. That's the axial force. I call it N. That's 2400 pounds. I have a V sub X, which is a 1200, as you could see here, and I have a V sub Y, which is the 3600 here. Okay? Now, the moment of the 1200, you could see that this guy creates a moment about y-axis like that. So that's 1200 times the distance of 16 inches, right? This distance. So 19,200, and look at the way moment of about y-axis is going to act. It's going to act as you could see here. Let me redraw it again one more time for you. And then this 3600 force creates a moment about x-axis like that, right? So that moment would be 3600 times 12 inches, this distance. Okay, so 43,200. But now, before we move to the next page and try to find the stresses due to bending and also due to the axial load, notice that this moment about x-axis, this guy puts point K in complete tension, MC over I, moment about x-axis times C divided by I sub x. But and then also creates tension for point H because that's above the neutral axis. Remember, this is the neutral axis right here, right? So we have to use a Y of 2 inches for that. So so this is, of course, due to M sub x. But due to M sub y, point K is right on the neutral axis, right? And it doesn't feel anything, but point H would be in compression. You see how M sub y is causing this to be in, point H to be in compression, right? It's pushing in. All right, let's move to the next page. I have redrawn this picture so we can refer to it again. So look, I went and I calculated I sub x and I sub y. And the whole point of this problem is to show you that in this equation, when you try to use the Fletcher formula, if you're using moment about x-axis, you have to use I sub x. If you have moment about y-axis, you have to use I sub y. That's very important. When we have a circular cross-section, we don't have to worry too much about that because of the symmetry of the circle, but not for rectangular cross-sections. Okay, so we already have the moment of inertia, and we have also the area, which is a 4 by 6, 24 inches squared. So let's go ahead and find sigma at K. So a minute ago, I just said that due to this guy, M sub x, point K is in tension. So that would be M sub x C, where C is this, right? From the neutral axis to the top fiber divided by I sub x. By the way, all points on this cross section, they feel the same due to what? Due to this normal force here. Due to this normal force, right? So you have to again think that everything is going to be in compression. All the points. Point K is going to be in compression, point H. So that's why I have minus n over A for both K and H. Okay, so that would take care of sigma at K. What about sigma at H? Besides minus n over A, a minute ago I said that due to this m sub y, this guy is going to be in compression, but my c over I, this time this is c, by the way, which is 2 inches. And then also due to m sub x, this green moment here, this point is in tension. And you have to use the y equation, not the maximum equation, not the mc over I, but rather the general equation. All right, plug in your numbers. You see that actually sigma k is much larger than sigma at H. Actually, this becomes minus 100 here, and this becomes 1200, minus 1200, and this is actually becomes 1200. So in a way, they cancel one another. Okay, so that takes care of the normal stress. Let's move and talk about shear stress. Okay, we have two shear load. Now notice that obviously we don't have any twisting here of this rectangular, cantilever beam. And even if you had twisting, you guys remember that the TC over J, tau max equal TC over J, only applies to circular section. For non-circular section, we have to have a table to figure out the stresses. Anyways, so the only stress we have here is the transverse shear stress. So let's look at it individual shear load. So due to V sub x, right, due to this guy, V sub x, notice that the shear stress becomes maximum at K, as shown here in the picture, and 0 here and 0 here. All right, so tau at H is 0 and tau at K is a maximum. So no reason for me to use VQ over IT, not a good idea, right? Don't use that. Instead use what? Instead use 3/2 V over A. So we can calculate that and you get 75. But now what happens if we look at V sub Y? Due to V sub Y, right? Notice that this time tau at K becomes 0 and tau here is 0, but tau here is maximum. If you had a point here, it would have been maximum. And it would have been 3/2 V sub Y over A. But look, point H is not as the maximum, it's not on the centroid. Therefore, we have to use the VQ over IT. And I call this Q sub H here, by the way. So V obviously is V sub Y, Q sub H. But be careful, guys. You have to use I sub X here. So these don't match. See, if at moment they do match. All right, moment is a different story. But just remember that shear load is, for the shear load, you use always the moment of inertia perpendicular to that, in the direction perpendicular to that. Okay, let's go ahead and calculate Q sub H. You guys remember that Q is, in a way, summation of A, Y. But in this case, you only shade the area to the nearest fiber. This is a 4. And this is a 1. Remember, that's 1 inch. So area becomes 4 inches square. And what is Y bar? Y bar is always the distance from the centroid to the neutral axis. So that's Y bar, which becomes 2.5. Half inch here and 2 inch here. Okay, 10 inch cube. Plug in 3610, I sub X 72. And what is T? T is the wet, which is 4 inches, as you could see. All right, find tau sub H. So I just summarize all our numbers here, sigma H, sigma K, and tau H and tau K. The last thing I want to show you is just the way the stress element for these points are going to look like. So I have shown you here. Notice that due to this guy, see this is stress, this M sub X is pulling on it, and this M sub Y is due to this M sub Y and also M sub X. Eventually we get a compressive one. So they are shown here. H is in compression due to normal stress, and by the way, these are the Z direction. Remember, this was the Z direction. That's why I call it sigma Z. All right, and then The shear stresses, the direction you could figure out. See, that's how I have that direction here. See that? And direction for visa, direction for tau sub h is downwards here, like that, because v sub y is downward. So that's why it's downward, shown here, 75 and 125. By the way, you could also draw the three-dimensional stress element if you want. I can do it here for you. So for example, if you look at point K, and you want to make this a three-dimensional stress element, let me erase part of this here so I can show you what's going on. Okay, so this is what we have. Basically what I'm doing, I'm just making this a three-dimensional stress element. So you see, basically you have sigma z, your sigma z, let me put the same color, that's your 1700. As you could see, this point is in critical, I mean, compared to the other point, h is more stressed. All right, in terms of the sign convention for the tau, you guys remember this was x, this was y, this was z. I'm sorry, this was, I don't want to confuse you. This was z, this was y, right? So this tau would be, let's see, what would be this tau here? This tau is on the x side, right? Remember the first subscript is the side. And in what direction? Z direction. This is tau xz. This tau would be tau zx. And of course, the same thing will happen on the back face here, and the side face, and one in the back face as shown here. So basically, this is the three-dimensional version of what I have here for you. Okay, and these, I believe, they become tau sub zy. Yeah, if you draw a three-dimensional stress element for this guy. All right. As always, thanks for watching and listening, and this hopefully should give you a better idea about combined loading problems.